Welcome to JavaScript, the Wibbly-Wobbly Timey-Wimey parts. I am a fan of Doctor Who, that's where this is coming from. But this talk is about JavaScript, okay? At its core, JavaScript is a synchronous blocking single-threaded language. This means that JavaScript can only do one thing at a time. When people say that JavaScript is an asynchronous language, what they mean is that it can manipulate JavaScript to behave asynchronously. Okay, you'll see on here a list of boundaries of asynchronous activity: user interaction, network I/O, disk I/O, inter-process communication, timers. These are all things that really mess with a single-threaded blocking synchronous language. Okay. What I want to talk about in this talk is, how do we do that? How does JavaScript do that? So, about me. I've been writing code since I was 10 years old, so I just passed 45 years of writing code. Coming out of college, I got work teaching computers. So for about the next 25 years or so, I taught computers. A lot of what I taught was programming in there as well. About 12 years ago, pushing 13 years now, got an opportunity to get back into writing code, and clearly remembered my love and passion for writing code. I am a husband and father of two amazing children. I have a background in corrections with the U.S. Army Recruiting Command. I've worked with Select Sires, a company in Plain City, Ohio, that provides bull semen to the AI industry, artificial insemination. I'm a senior solutions developer with Leading Edge, a company out of Columbus, Ohio, that solves problems. I'm a senior solutions developer. We solve problems. Okay. My contact information is on here. Feel free to contact me if you like. So let's get into the talk. Some definitions. Parallelism is multi-threaded processing. Things get scheduled at the same time. Okay. Asynchronous. In terms of what we're talking about here, asynchronous is a single thread with an event loop. Okay, event loop can control things outside of that synchronous time. This is managed by concurrency. Higher level tasks can occur within the same time frame. Code in the queue has some level of control over what happens next in the queue. We hope for contention, multiple things that need to occur at the same instant. So basic definitions, these are going to carry forward as we look at the rest of this talk. Let's talk about the JavaScript engine details. Okay. These details are not a part of JavaScript, not a part of its engine. They're included in the browser or in the Node.js runtime environment, depending on where you're running your JavaScript code. setTimeout is a part of the browser. The event loop, the web APIs, the message queue, the task queue are all controlled by the browser. The browser has multiple threads available to it. The JavaScript engine gets one. So here's what you see when you search for browser queues. Okay, we have an event loop that has a heap and a stack, and the heap contains the object, the stack are the variables and the functions, and the JavaScript runtime hands things off. Web APIs for Ajax, for the DOM, for whatever. And as those things complete, or as the timing hits right, it gets pushed onto the callback queue. And as JavaScript has time, it takes a look at that callback queue to see what it can do, what it's allowed to do. So you've probably heard of Callback Hell somewhere along the way. And, our pyramid of doom in our code, where you see that big arrow pointing to the right, is a symptom of a problem. It's not the real issue. The real issue comes down to inversion of control, a trust point when a callback is passed. Does that code behave as expected? Okay. A lot of the reason here is temporal dependency, requiring nesting, nonlinear thinking. And that's where these pyramids come from. Promise, hell, pyramid of doom, inversion control. Okay, these are difficult things to reason about because things don't happen linear and our brain is used to working linearly. Some of the considerations: coordination of data at a higher level, being able to track data across those callbacks, split callbacks, separation of success and error. This is what promises do. Errors first. Again, the same trust issues you have with split callbacks. With promise hell, the flow control is styled badly. It's hard to read and understand. Nesting promises rather than vertical chaining. And a lot of problems come in when people don't have that vertical chaining right. So now let's get into what we're going to do here, okay? We're going to do a thought exercise first. I want to get you used to what I'm doing here on the right. You'll see some code that's kind of been sitting there. And we're going to use the terminal space pretty heavily, okay? We're going to go through synchronous code, non-asynchronous code. We're going to go through simple network code, complex network code. We're going to go through simple promises that came about in ES 2015, as well as some complex promise code. We're also going to take a look at generator throttling, user interactions, web listeners, web workers. We're going to look at timing code, race conditions. We're going to look at set timeout timer and ES 2017's async await. So, thought exercise. Let's show some code here. And what do we expect this code to do? Well, let's take a look at the code. We have a variable time of 10,000 milliseconds. We have a function for change color that grabs a wrapper, document element get by thought wrapper. It styles the background color to red. We have a change layout function that grabs a paragraph tag, sets its attribute to its ID to thought run, sets the inner text to thought exercise, and appends that to a wrapper. Okay. We have a wait function that gets a date and runs a while loop, checking to see if the current date is less than the start date plus the time, which is the 10,000 milliseconds. We have an event that runs the change color function, runs the change layout function, runs the wait function. Now I split these up like this to make them easier to read here in the terminal. One of the limitations in the terminal is you go beyond 5 lines, it truncates, and I want to truncate, okay? So we have a start. This is where we need to decide what's going to happen, right? We grab the button, we remove the hide, and we click on the button. Okay, which triggers event. That's that change color, change layout, and wait. So the thought exercise is, what do you think that's going to do? Okay, we're triggering the change color, change layout, and wait. And I get several different answers as I do this presentation live. Is it going to display the text and the color? Is it going to wait that 10 seconds? Well, I don't know. Well, I do know, but I don't know. Let's find out. Okay. So we have a click me that shows up, and it's been clicked. There we go. So what happened is we had that while loop in that wait that was thread locking. Okay. Even though it ran third, everything else got put on hold because JavaScript itself was thread locked. Only one thing could happen at a time. It was stuck inside that while loop. Okay. Thankfully, the while loop ended. All right, so let's take a look at some non-asynchronous code. And here we've got an array. We've got a for each sync, we've got a for each async, we've got run sync, we've got run async, we've got a start, we've got a debug. Okay. The start can allow this to run through the async route or the non-async route based on a variable we pass in on start. Okay. Let's assume we're going to run the non-async first. And what I want you to see here is the non-async, which means async is false, is going to run the sync, one that's called run sync. Okay, so that's the next one up here. Run sync console logs the start. It runs a for each async. Inside that, passing numbers, which is that array of 1, 2, 3, and a function. It takes a number and console logs the number times 2, and then the end. Okay. Sorry, I read the async. The run sync is the next one up from that, where it's going to do a start. It's going to do something similar, but it's going to use a for each sync. Okay, so let's take a look at our sync and our async. Our sync is just a for loop, firing the callback, passing the item in as it loops through. The for each async wraps us in a set timeout of 0 milliseconds, passing the item in through that set timeout. Okay, so what we've got to think about here is if we run this synchronously, what do we expect to see? In my mind, as I look at that run sync, I would expect the start 2, 4, 6, the end. Should. Okay, so let's run this non-async and see what happens. Exactly as I expected. Okay, now the async. Do we think we're going to get the same thing on async? Let's go back to show or clean up our code. Okay, it's wrapped it in a set timeout. But it's a 0 millisecond set timeout. Let's run this. Interesting. Okay, this gives us the start, the end, 2, 4, 6. So this is one of the first places I started to question what's happening in the set timeout. That's a 0 millisecond set timeout. Because it takes time to put things onto those event loops and pass things around, my guess is this is taking it longer than 0 milliseconds to run. Okay, doesn't count what's inside the set timeout as part of the active code immediately. Okay, JavaScript goes back to get that when it's done, which is after it console logged to the end. There is a piece of this talk I used to do on showing async and the debug and that kind of things with pauses and that, because you used to have to turn it on. It's now on by default. So if I put a breakpoint inside that for each sync or inside the set timeout, you'd actually see it shows you async. It's default built into the Chromium base. Okay. So let's take a look next at a simple network. Let's take a look at our code. Should be getting used to this at this point. And this is a really simple network request. We got a start and an end on the start down there. It fires network request. Network request has a set timeout, 10 seconds. Okay, and this async code should fire when the set timeout finishes at 10 seconds. So we should expect, it should be pretty easy to glance at this and say, okay, I'm going to see the start and the end. I'm going to see a wait of 10 seconds. I'm going to click this now because the start and the end is there. And then I've got to talk and juggle a little bit to get us to that 10-second window to see that pop up. Okay, I'm talking really fast, so I got to juggle. There we go, after 10,000 milliseconds. Okay. Pretty straightforward there. That got handed off to the browser. That set timeout got handed off to the browser. the JavaScript was going and looking at that event loop saying, hey, I'm not doing anything. And eventually it popped up and it put it back into the queue so the JavaScript could pick it up. Somewhere around the 10,000 millisecond point. Let's take our complexity up a layer. Okay. So here we console 1, we console 5. We execute the function first. First has a set timeout. Inside that, we've got a console 2, console 4, and it's firing second. Second has a set timeout, and inside its set timeout is console log 3. With our time on those set to 0. Okay, so these are set timeouts that run very quickly. Guesses could be anywhere along the lines of 1, 2, 3, 4, 5. Could be 1, 5, 2, 4, 3. Could be 1, 5, 2, 3, 4. Probably not too many other orders than that. So let's start this one and see what happens. It should be pretty quick. 1, 5, 2, 4, 3. So the set timeout for first finishes before the set timeout of second, which pushes the 3 down as the last one. The console log 1 and 5 were not inside set timeout, so they triggered immediately, as JavaScript had time, clearly. Now let's take a look at a simple promise. Let's look at some code here. And we've got to start. Console log start, console log end. We've got a timeout and a promise that get triggered. The timeout has a set time of 0, set timeout fired. The promise resolves immediately. Then it console logs or it errors. Since we didn't reject, we're not going to trigger the error branch, but okay. So the question becomes, are we going to see the start resolved, set timeout fired the end? Are we going to see the start and the end, set timeout fired, resolved? Or are we going to see the start and the end, resolved, set timeout fired? Some of this is going to depend on how the browser handles set timeout versus promises. So let's see what happens on this simple promise. So we see the start, the end, kind of what we expected, resolved. The promise, even though it triggered after the set timeout, finished first. The promise is managed by JavaScript. Okay, but at some level, its priority is a little bit lower than the active code, which is why the end triggered before it. And then the set timeout clearly had to wait until JavaScript had some time to go check the loop. Let's step it up a notch with our promises. And if we look at our start, we have a set timeout, or sorry, we have a timeout function that runs between the start and the end. We have a promise 1 and a promise 2. Our timeout looks like a regular timeout. Okay, our promise 1 resolves and console logs. Our promise 2 resolves, console logs, and triggers a promise 3. And promise 3 resolves and console logs the result. So we got all kinds of things that could happen here. My guess is, just quickly glancing at this, and I haven't run this talk in a while, so I'm guessing just a little bit. The set timeout is probably going to be last. The promise 1 is going to finish. The promise 2 is going to finish in console. The promise 3 is going to finish in console, then the timeout will finish. Let's run it and figure it and see what happens, okay? We were right, 1, 2, 3, after the start end, and the set timeout fired. Okay. Pretty cool stuff. Now let's dig into some interesting stuff, generators. I spent quite a while digging into generators. And this is one example I got, but I wanted to look into throttling, okay? So I'm setting up a throttle that should have a 3,000 millisecond delay, a 3-second delay. Okay, you have to do the thr.next. You have to fire the first next on your throttle to kind of initialize things. Okay, and I have code set up so that I can trigger the throttle repeatedly And what will happen is we'll do the throttle start, and you'll see the code starting, and I'm firing it over and over again. And now I'm sending comments. Okay, and nothing happens. And actually, it is resetting our 3-second delay until it can hit the end there and finally send a final comment to the console log. Okay, the throttle does some interesting things, and we were playing with the throttle and the set timeout and how it allows us to handle things. This is a syntactic form of a state machine. Okay, it's about solving the reasoning about issue. It allows us a non-run to completion behavior with localized blocking. Okay, these generators return an iterator. This is something we can loop over. The throttle was an interesting exercise here to see the delay and how that worked. Let's go back to a simpler example here. And let's take a look at user interaction. Okay, so I'm going to show the code here and drag start, drag over, drop. Okay, we're console logging within these, so you can see what happens when we drag start, drag over, and drop. And it's really interesting because, if I come over here and I click this and I start to drag, you're seeing the drag overs. Okay, and somewhere up there we have the drag, and I'm going to drop it. Let's say drop it down there. Okay, you see the drop drag triggered. These are all our little interactions. I did a lot of them on this one. Sorry, we'll go back up to the top here, and you can see the drag start. Okay, so this was the drag start that fired here. You saw drag overs fire console logs at various times, and it didn't when I was on top of it. And then the drop. Okay, and this is actually kind of where I realized something when I was looking at my code. There was something that came up. I'm going to pop over here and show the code. Clear this. There we go. What I realized was our console log is a browser set of functionality. It's got its own thread. This is where I started to see that. Okay, and you'll see later where I get into that a little bit further. So now let's take a look at event listeners. Okay. And we'll take a look at the code real fast on our event listeners. I do have to click that for the listener stuff to trigger out, but we have a start that grabs this event listener link, sets up listeners, triggers listeners. So our setup listeners listens for a click, okay, and passes to output the click handler. And a second one, so it actually attaches two event listeners, okay. To see what happens with the click handler 1 and 2, we have a trigger listeners that console logs start and end and then clicks the button. Okay, so we're going to do something with this button, and we'll see a start and end. The question becomes, when do we see the click handler 1 and the click handler 2? This tells us something interesting. So let's come out here and initialize this. And here we go. So at our code 9 start, we have the start, click handler 1, click handler 2 in the end. This is different than the asynchronous code we've been looking at. Event listeners are synchronous, not asynchronous. Okay, now it's kind of a surprise to see that. Now let's move on here, and let's take a look at web workers. Okay, and here I've set up a little pattern. And what I want you to see here is let's look at the start, and I can pass in synchronous or asynchronous. We're going to try the sync first. If you look at the run sync, it does an inline progress. It grabs the ID and does crunch numbers inline. So crunch number inline loops through, passing step times 10 into the callback. So it's looking through 10 times. So it should do a 0, 10, 20, 30, 40, all the way up to 100. And we have a 1 second delay in between. Okay, and this is our thread lock delay. And in the async, we'll take a look at that in a minute, but this display percent is really kind of the key we have in here inline, where it's going to do some console logs. And this is the other place that I saw that, console did some things I didn't expect. So let's start this up and see what happens to our inline. Okay, there's 0, there's 10, there's 20, there's 30, there's 40, right? It's just doing the inline percents, just like we expected in the display inline. Hits 100, and our bar changes. And anybody that's dealt with percentages on as a process runs would be somewhat familiar with this. Okay, it didn't display till it hit 100, till the thread locking was done. The thread locking was so fast, JavaScript couldn't do that callback. It couldn't properly update the inline progress value. Okay, this one's a little different because what I did say, web workers. So let's take a look at our async code. And I do have a web worker, and our work, you can see here, we've attached the worker. So we get on message on error. Okay, we have worker progress. We can crunch numbers. We're displaying percentages. We have a run async that grabs the element that posts a message to start. The vast majority of this code is doing the same thing, crunching numbers, but as a web worker. Web worker gets its own thread. So we see things a little bit differently here. So let's start the asynchronous version here. And you can see our bar is changing as our percentages change. Separate threads. It has the exact same thread locking and loop in the web worker. So it was kind of cool to see that, kind of good to realize that we can do some other things with those web workers than we expected originally. Now, on this next one, I'm going to cross my fingers because occasionally this one fails on me, and it worked as I expected. And this is related to thread locking, race conditions, or sorry, not thread locking, race conditions and timing of our code. Okay, so our original content is actually loaded with JavaScript, is loaded before the DOM is finished updating, whereas the change content's loaded after. Okay, occasionally this breaks on me. I don't know why. It's race conditions. It is possible that both of these could get changed correctly if the DOM updates quick enough. But that's what it is. That's why we put our JavaScript files at the bottom of the body, so that we know the DOM is updated correctly, initialized correctly. Okay. All right. Set timeout timer. This is one that I've recently seen some comments from folks that have dug into, some changes in the individual browsers and things like that. And I don't have the documentation right here with it. I'll try and attach that if I can find it to the original video when this is uploaded. But I had this question in the back of my mind, and it was, what is the set timeout? I could put 0 in, but other things are able to run first. And so I set up a delay testing. You can see here, I set up the time at 10,000. Oh, we haven't shown our code yet. I said our current repetitions is 0, total should be 1,000. Okay. If you pull my code down, be careful with that one. My first time I ran this was to set it to 100,000 to give me good averages. Okay. Because I wanted to get how long it took. And man, it thread locked like crazy. I mean, I had to manually shut down my browser. I had to go through some hoops to shut down my browser. I set a delay, total actual delay. So this code in here essentially is going to run 1,000 set timeouts and tell us what the actual delay is. Okay. So I'm going to start this testing with it running with 0 milliseconds, and it's going to run through 1,000 repetitions with a 0 millisecond delay. And you can see we came back at 4.394. I have found out, looking through documentation, the average for most browsers is 4. There is talk of, depending on the number of set timeouts that are running at any given time, That could jump up, that could jump down. If you've only got one set timeout, it might actually run really close to 0. But the other thing I need to point out here is, irregardless of what the delay is, this one's probably 4. But you never run at 4 milliseconds. Sometimes it's after that. And it's probably after that. It runs when JavaScript has time to get to it. Okay. So let's try this with a 10 millisecond delay and see what the difference is. And this is going to take a little bit longer. These are 10 millisecond delays. And see what happens, right? So we're taking that delay, we change that delay. It clearly is taking a little bit longer to run, and I'm trying to juggle and talk, and here we go. So our 10 millisecond delay average is closer to 16 milliseconds. Okay, that's a pretty hefty difference between the 10 that you expected. If you expect it to come back at the exact time, it'll never happen. Okay. So things have changed on set timeout a bit, but you can still see that, you know, it doesn't do what we as developers thought in the back of our head a lot of times. So let's move forward here. And let's take a look at ES 2017's async await. Okay, let's show our code. And so in the start here, we have a resolve. We set to resolve state. We're going to console log the start. We're going to start the async await. We're going to console log the end. Okay, so we're starting the async await. So if we look up at async await, it is an asynchronous function with a try catch, and we're console logging, awaiting the async process. And then we console log error if it passes through the error loop. Okay, async process returns a promise with a resolve reject inside a set timeout. This time is set to 2 seconds. And if resolve is set to this, if underscore resolve is set to true, we resolve, otherwise we fail. I've got this set up so I can run it both ways. Okay, so see the resolve state coming in up at the top. So, you know, the question then becomes, which message are we going to see as we pass it through, and what timing? It's probably going to be the start, the end, and then the success and the failure. But let's see. Let's try it with a resolve. You see the start, the end fires, and it did something after 2 seconds. Let's try the reject branch, and we see the same thing, but it fails after 2 seconds. You know, the failure is not necessarily immediate. Okay, that's one that I wanted to point out here. The nice part of async await is that it expands on the user promises. It essentially unwraps a promise, writing asynchronous code that looks and feels synchronous. So what you see in the async await versus the async process, that async await is much easier to read. We don't have all that heavy chaining built into it. It cleans up that syntax, makes it significantly more readable for us. Now, let's move forward here and summarize. Okay, you've seen all of the various issues, problems, and things that can come up relating to asynchronous code. We've examined sync and async using callbacks. We've looked at ES 2015 promise chains. We've looked at generator throttling, user interactions. We've looked at event listeners that are surprisingly synchronous. We looked at web workers, load timing. We've looked at ES 2017's async await. Covered a lot of ground here in the Wibbly-Wobbly Timey-Wimey parts. Thank you.